If you want a glimpse of Marie Curie's manuscripts, you'll have to sign a waiver and put on protective gear to shield yourself from radiation contamination. Madame Curie's remains, too, were interred in a lead-lined coffin, keeping the radiation that was the heart of her research, and likely the cause of her death, well contained. Growing up in Warsaw, in Russian-occupied Poland, the young Marie, originally named Maria Skłodowska, was a brilliant student, but she faced some challenging barriers. As a woman, she was barred from pursuing higher education, so, in an act of defiance, Marie enrolled in the Floating University, a secret institution that provided clandestine education to Polish youth. By saving money and working as a governess and tutor, she eventually was able to move to Paris to study at the reputed Sorbonne. There, Marie earned both a physics and mathematics degree, surviving largely on bread and tea and sometimes fainting from near starvation. In Paris, Marie met the physicist Pierre Curie, who shared his lab and his heart with her. But she longed to be back in Poland. Upon her return to Warsaw, though, she found that securing an academic position as a woman remained a challenge. All was not lost. Back in Paris, the lovelorn Pierre was waiting, and the pair quickly married and became a formidable scientific team. Another physicist's work sparked Marie Curie's interest. In 1896, Henri Becquerel discovered that uranium spontaneously emitted a mysterious X-ray-like radiation that could interact with photographic film. Curie soon found that the element thorium emitted similar radiation. Most importantly, the strength of the radiation depended solely on the element's quantity and was not affected by physical or chemical changes. This led her to conclude that radiation was coming from something fundamental within the atoms of each element. The idea was radical and helped to disprove the long-standing model of atoms as indivisible objects. Next, by focusing on a super radioactive ore called pitchblende, the Curies realized that uranium alone couldn't be creating all the radiation. So, were there other radioactive elements that might be responsible? In 1898, they reported two new elements: polonium, named for Marie's native Poland, and radium, the Latin word for ray. They also coined the term radioactivity along the way. By 1902, the Curies had extracted 1/10 of a gram of pure radium chloride salt from several tons of pitchblende, an incredible feat at the time. Later that year, Pierre Curie and Henri Becquerel were nominated for the Nobel Prize in Physics, but Marie was overlooked. Pierre took a stand in support of his wife's well-earned recognition. And so both of the Curies and Becquerel shared the 1903 Nobel Prize, making Marie Curie the first female Nobel laureate. Well-funded and well-respected, the Curies were on a roll. But tragedy struck in 1906 when Pierre was crushed by a horse-drawn cart as he crossed a busy intersection. Marie, devastated, immersed herself in her research and took over Pierre's teaching position at the Sorbonne, becoming the school's first female professor. Her solo work was fruitful. In 1911, she won yet another Nobel, this time in chemistry for her earlier discovery of radium and polonium, and her extraction and analysis of pure radium and its compounds. This made her the first, and to this date only, person to win Nobel Prizes in 2 different sciences. Professor Curie put her discoveries to work, changing the landscape of medical research and treatments. She opened mobile radiology units during World War I and investigated radiation's effects on tumors. However, these benefits to humanity may have come at a high personal cost. Curie died in 1934 of a bone marrow disease, which many today think was caused by her radiation exposure. Marie Curie's revolutionary research laid the groundwork for our understanding of physics and chemistry, blazing trails in oncology, technology, medicine, and nuclear physics, to name a few. For good or ill, her discoveries in radiation launched a new era, unearthing some of science's greatest secrets.
If you were walking down the road and you saw this can outside your house, what would you think? Radiation is something that makes us feel very, very uneasy. But what do we mean when we say radiation? Radiation comes from part of the atom called the nucleus. The nucleus is made up of neutrons and protons, and it's the center of the atom. Usually this is stable, but if it gives off radiation, we call this unstable. An unstable nucleus will give off pieces of itself. If the atom gives off radiation, we call it radioactive, and it can either give off radiation in the form of energy or in the form of a particle. This type of atom we call radioactive, and the actual atoms are called radioisotopes. Most atoms are not radioisotopes because they are completely stable.
When a nucleus is very big, it becomes unstable. It's a bit like when you build a sandcastle, and when you get a really big sandcastle, the last bit of sand just keeps falling off. That last bit of sand is a bit like an alpha particle. You put it in, and eventually, bang, it comes shooting out. So what is an alpha particle? How do we know they're there? What do they leave behind in the nucleus? These are all questions that we're going to try and answer. Let's look at how to build a really big nucleus first. You may not know this, but most of the most common atoms have a mass number which is a multiple of 4, and a proton number which is a multiple of 2. Let's look at helium first. Helium has got a mass number of 4, a proton number of 2. Now let's go on to carbon. Carbon has got a mass number of 12, and it's got a proton number of 6. So it could be made up of 3 of these blocks of 2 neutrons and 2 protons. Then finally, let's look at oxygen. Oxygen has got a mass number of 16 and a proton number of 8, and it can be made up of 4 of these building blocks. This is because the easiest way to build a bigger and bigger nucleus is to add 2 protons and 2 neutrons at the same time, just like this block here. So if you can imagine, if you've got a really big nucleus that's so big that it starts to become wobbly or unstable, and bang, out comes 2 protons and 2 neutrons together in an alpha particle. So there you have it. An alpha particle is 2 protons and 2 neutrons. It's the heaviest type of radiation, and the 2 protons give it a charge of +2. 1, 2. Also, because it's very heavy, it travels slower than other particles. Well, in particle terms anyway. They come out of the nucleus at 30,000 kilometers per second. You might find that a bit fast, but wait till you see the other particles. You can use these properties to detect alpha radiation. Because it is big and has a large charge, you can make it move through an electric field. So here's your alpha particle coming out of the nucleus, and it's going through an electric field. As it goes through, it bends. If it comes across another atom, it's pretty likely to take an electron with it. Here's the alpha particle, here's an atom. The alpha particle comes across it. As it gets near, it starts to make it wobble a bit, and as it comes away, it pulls off an electron with it. This makes it very, very ionizing. However, it also loses energy more quickly than the other particles, so it slows down and eventually stops. This means it's not very penetrating. You can even stop it with tissue paper. Once you stop it, it sits and waits for a couple of electrons. So remember we said it's got 2 protons and 2 neutrons? When it gathers those electrons, it becomes a helium nucleus, which is pretty harmless. So there you have it. An alpha particle is a helium nucleus, waiting for 2 electrons. What about the nucleus it leaves behind? This nucleus is called the daughter nucleus. This has lost 2 protons and 2 neutrons. The newly formed daughter nucleus loses 4 in its mass number and 2 in its proton number.
This video is going to give you a brief introduction to beta minus decay. To begin with, let's look at the notation. So I've got the element which I've just wiggled as x, and to the left of that I'm going to write the number of nucleons over the number of protons. The nucleons are all the particles in the nucleus, and the protons, of course, they're the protons. As an example, let's look at a helium molecule. So in a helium, I have 2 electrons, 2 protons, 2 neutrons. That means I'm going to have 4 nucleons, and I'm going to have 2 protons, and the helium is element abbreviated with as He. So 4 over 2 He. Now let's look at a decay, a beta minus decay. So I'm going to start by looking at carbon. In fact, I'm going to look at carbon 14. So I got 14 nucleons. You can't see them all in my model. And I've got 6 protons of the 14 nucleons. And of course, C is a symbol for carbon, so 14 over 6 carbon. And that's going to, when it goes through beta minus decay, 2 products are going to come off of this. The first one's going to be an electron with a negative charge. That's why it's called beta minus. The second one is going to be something, a little piece of energy, and it's called an antineutrino. The electron comes with an antineutrino. This doesn't have charge, and its mass is so incredibly small that for all practical purposes, it's no mass. Just think of it as a little piece of energy coming off of this. Now the electron is not a nucleon. So it's not a nucleon, it's not found in the nucleus, so that's going to get a 0 to the left of it. But it does have a charge of -1, that is -1 times a proton. So its charge is going to be -1. And that's how I'm going to write the symbol for the electron in my equation. So I've got 14 over 6 carbon, and that's going to turn into, well, my 2 products here, which is going to be an electron, 0 of -1, and an antineutrino. Now let's balance this equation. If I look at conservation of mass, I'm going to have 14 nucleons. On the right hand side, I've got 0 for the electrons. So what plus 0 is equal to 14? Well, just 14. On the bottom, that's to be conservation of charge. I've got 6 positive charges on the left. I've got -1 on the right. So what -1 equals 6? That will be 7. So if anything with 7 protons, that's going to be nitrogen from our periodic table. So where do these elements come from for this beta minus decay? Well, it comes from a neutron that transforms into a proton, an electron, and an antineutrino. So on the left-hand side of this balancing equation, on the left-hand side, that's a neutron. And when the neutron creates the proton, it's also got to create a negative charge because you have to conserve charge. So it starts off as neutral on the left, and then on the right I added 1 plus charge, that was the proton for the nitrogen, and then 1 minus, and that was the electron. And then what's left over is a little bit of energy, and that's the antineutrino. This video is going to be a brief introduction to gamma decay. To begin with, let's look at a little notation. I'll start with my material, my substance, my element, and that's going to be the X that I've just wiggled. Next to that, I'm going to write the number of nucleons and then the number of protons underneath that. It's not a fraction, it's just one number over top of another. Let's show you how it works with a helium molecule. So in helium, I have 2 electrons, 2 protons, and 2 neutrons. So I got 4 nucleons in the middle, and 2 of which are protons. So it's 4 over 2 helium. Alright, let's move along to something that goes through gamma decay, and that'll be a radioactive or an excited state of iodine. So it's not regular iodine, it's an excited state of iodine. And what happens is this excited state will then lose energy and give off a high energy gamma photon. So to represent that, we write this as 123 nucleons over 53 protons, I for iodine, and we put a little asterisk. And the asterisk means that it's on an excited state. In other words, it has too much energy and it's unstable. To stabilize the iodine, what it's going to do is it's going to give off a photon. And this photon is going to be in the gamma range. It's going to be a really high energy photon. This photon has so much energy it'll go right through you. Alpha particles will stop through your clothing, beta goes somewhere into your body, but the gamma goes right through you and other people around you. So it's a very high energy particle. And gammas don't have any charge, and our moving photons also don't have any mass. So when I conserve mass, there's really nothing to do. It's just going to be 123. And when I conserve charge on the bottom, it's still going to be 53. So my product when I'm done, or my daughter element, is going to be iodine. The same thing I start with, just with less energy.
Alpha, beta, and gamma radiations. Certain elements exhibit spontaneous emissions of radiations. Such substances are called radioactive substances. Here, one can observe the emission of the 3 major types of rays emanating from a radioactive substance placed inside a lead block. These 3 rays get deflected in different directions in an electrostatic field. The rays that get deflected towards the negatively charged plate are called alpha rays, while those that deflect towards the positively charged plate are called beta rays. The rays that travel straight without deflection are called gamma rays. The alpha rays are slightly heavier and move with relatively less velocity. They have less penetrating power and can be stopped by a simple barrier like a sheet of paper. The beta rays are less heavy than alpha rays and move with a relatively higher velocity. They have more penetrating power. They can pass through paper but can be stopped by a barrier like an aluminium foil. The gamma rays move with a very high velocity. They have high penetrating power. They can pass through a thick aluminium foil but cannot pass through lead. Alpha rays are made of positively charged particles with a net charge of +2. They have high ionizing power. The beta rays are made of negatively charged particles with a charge equivalent to that of an electron. They have less ionizing power. The gamma rays are not made up of any particles. They have the least ionizing power. They are electromagnetic radiations.
This atom has an unstable nucleus. Any moment now, it may undergo radioactive decay. Any time now. Or it may not. We just don't know, as decay is a random event. We cannot predict when any single nucleus will decay. But we can say, if we have a large enough number of atoms, then decay will happen somewhere in a sample. If we time how long it takes for half of the atoms to undergo decay, we have a measure, half-life, of a rate of decay. You have just seen about half of the atoms decay, and it took 5 seconds. So the half-life is 5 seconds. How long will it take for half of the atoms that have not yet changed to decay? Did you say 5 seconds? Yes. In this case, the number of original atoms halves every 5 seconds. You could have a bucket of 100 dice, and after each emptying of the bucket, remove all the ones that show a 6. Repeat until you have about 50 dice left. How long did it take? That's 1 half-life. If you recorded the time it took for your sample of dice to halve each time, you would get a graph like this. Each halving of the numbers is 1 half-life. The graph shows 6 half-lives. Half-lives can be as short as nanoseconds or as long as billions of years. If we record the radioactivity of a material over time with a Geiger-Müller tube and a counter, then we can plot activity, or a measure of the atoms decaying, against time to get a graph like this. The graph is for the isotope iodine-131. Notice how the count rate halves every 8 days, so we say it has a half-life of 8 days. Can you work out the half-life of this radioactive isotope? This is the decay curve for carbon-14, which all living things contain. It has a half-life of 5,730 years. Atmospheric carbon dioxide contains a small but constant percentage of radioactive C14, made by the action of cosmic rays on nitrogen molecules. This enters all living organisms via photosynthesis and subsequent food chains. While living, levels are constantly topped up, but upon death, the amount decays away. The ratio of C14 to C12 gives us a way of estimating how many half-lives have passed since death. For example, if a lump of wood contains only 25% of the original content of C14, then the wood has been dead for 2 half-lives, or 11,460 years. There is a limit to how far radiocarbon dating is reliable. After about 10 half-lives, or 55,000 years, there is so little C14 remaining that measuring it with any degree of accuracy is impossible. Short half-life radionuclides are used in medicine, so the patient is safe to go home in a few hours after dosage, whereas nuclear waste has a half-life of many tens of thousands of years. Most of the world's population have some strontium-90 in their skeleton, which originates from the atmospheric detonation of atomic weapons, mainly in the 1950s and 1960s. It has a half-life of 29 years. It will take well over 120 years before it begins to vanish from the Earth. But don't worry too much. We all have in our bodies radioactive isotopes we take in from our environment. For example, bananas supply us with very small amounts of radioactive potassium-40, which has a half-life of just over 1 billion years.
Please like and share our videos with your friends. If you have any questions that you want help with, just comment below.
Professor Dave here. Let's do some dating.
He knows a lot about the science stuff. Professor Dave explains.
In a previous tutorial, we learned all about the different nuclear reactions that nuclides can undergo, which helped us understand what radioactivity and radiation are. If this sounds unfamiliar, definitely check out that tutorial first, as all of that knowledge will be assumed in this one. If we are up to speed, then we now understand that various radioactive nuclei will decay at different rates depending on their half-lives, and we have developed a number of practical applications for this phenomenon in a variety of scientific and medical fields. One such application is something called radiometric dating. So let's learn about this now. Radiometric dating is a technique we have developed that takes our knowledge of the half-lives of various nuclei and uses that information to determine the age of a particular object, including things like fossils and ancient artifacts. A very common kind of radiometric dating utilizes carbon-14, a radioactive isotope of carbon, which is accurate in dating artifacts with an age of up to around 50,000 years. This is useful because carbon is such a common element, especially in living things, and anything with carbon atoms will have a trace amount of carbon-14. So this allows us to date a wide variety of objects. Carbon-14 forms in the upper atmosphere when nitrogen-14 collides with neutrons from cosmic rays in space. And although the vast majority of carbon is carbon-12, and most of the rest is carbon-13, there is a trace amount of carbon-14 anywhere there is carbon on Earth, including the carbon dioxide in the atmosphere. Carbon dioxide is absorbed by plants, and plants are eaten by animals, so living organisms, which are constantly bringing in material and expelling waste, will display the same ratio of carbon-12 to carbon-14 as is found in the atmosphere. But when an organism dies and all cellular processes come to a halt, no more material will be going in or out of that organism, so no new carbon-14 can become present, and all of the carbon is locked in place. Carbon-14 will then undergo beta emission to become nitrogen-14 again, thus gradually decreasing the amount of carbon-14 in the organism. And this process displays a half-life of 5,730 years. That means that if we find a wooden artifact made from a once living tree, and then use a mass spectrometer to determine that the ratio of carbon-14 to carbon-12 in that artifact is half of what it is in a currently living tree, that object must be around 5,730 years old, because half of the carbon-14 present when the wood was part of the living tree has already decayed. Of course, if any more than 10 or so half-lives have elapsed, this technique becomes less and less reliable. However, there are many other radioactive nuclei that we can use that have totally different half-lives and thus allow us to date objects of a wide variety of ages. Potassium, argon, lead, these all have radioactive isotopes that can be examined if an object in question contains appreciable amounts of that element. And many of these allow us to date objects much older than 50,000 years. Uranium-238 is commonly used to determine the age of certain rocks, including the oldest rocks on Earth, since this particular nuclide has a half-life of 4.5 billion years. Uranium-238 undergoes a decay series to produce lead-206, so we simply measure the ratio of uranium-238 to lead-206 in a rock to get its age. There are those who question the accuracy of such methods, and indeed there must be confidence that an object has not had its levels of these nuclei altered over time somehow, in order to trust the results of these techniques. But scientists are not naive. They know how to be rigorously empirical. Precision is enhanced dramatically when measurements are taken using two completely different radioactive nuclei. For example, if uranium dating is used to find that a rock is 3.62 million years old, and then lead dating is used to find that the same rock is 3.56 million years old, it is extremely unlikely that the rock is not approximately that age, because these are totally disparate materials, and the agreement of these measurements corroborates the age of the rock. These are the kinds of methods we have used to determine the approximate age of the Earth, which is around 4.6 billion years old. This is a value that really puts our existence into perspective and truly demonstrates the power of science in helping us understand the universe. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.